Speak up for the
Okay. Okay. So first of all, I'd like to thank the four organizers for inviting me to this good conference, and special thanks for Professor Kim, so local organizer, to take care of us very kindly. So I want to announce the title. So this is a joint work, Synchro A. Okay. So one of the fundamental issues of fluent dynamics in dissipative system is clarifying how the heterogeneity in the media influences the propagating manner of traveling fluent solution. Okay. So first, let's consider bistable reaction diffusion system in homogeneous media. Okay. So for this system, we have already known the existence of traveling fluent solution connecting two stable states. And the sign of velocity is determined depending on the strength of two stable states. Okay. So in this situation, such traveling front encounters heterogeneity or meets the heterogeneity. What kind of responses appear or output appears under the interaction between traveling front and heterogeneity? So we have many applications for such phenomena. For example, propagation of epidemic barriers, and the invasion problem for alien species, and the blocking of nerve impulse in nerve physiology, and finally, blocking for combustion wave in combustion problem. Okay. So let's begin with the following reaction diffusion system in homogeneous media. Okay. So this system contains two positive physical parameters, say epsilon and tau. So here, we assume epsilon is sufficiently small. Okay. So we divide the first equation by epsilon tau. So time constant of u equals 1, and here epsilon over tau, and here 1 over epsilon tau. So this assumption implies in this system, component U diffuse slower but react faster than the component B. Okay. So F and Z are reaction term. So here we use special nonlinearity F and Z like this. So very special. Then middle line of F is just piecewise linear, red line. Okay. And the middle line of G is also linear. Okay. So in this picture, red one and the blue one intersect at 3 points like this. So this system has a 3 constant solution. Okay? And for stability, G2 are stable, but middle one is unstable for this PDE system. So this system is called bistable system. So furthermore, we assume F and Z are order symmetric with respect to the origin. Okay? So this implies that two stable states have equal strength each other.
So here, U is the fast dynamics, am I right? U is fast dynamics.
Yes, fast dynamics. Yes, just right. Yeah. So if we divide this one, here is the 1 over epsilon. So epsilon is small. This function is very large. Okay, the first reaction. Okay. So here we assume we use the G special nonlinearity, but this can be considered as a typical example or more general bistable nonlinearity. So for this system, we consider traveling fluent solution connecting to a stable state. here. Okay. So now, introducing the moving coordinate z equal x minus ct, we can rewrite by using this coordinate, this system can be this one. Okay. So this is the ODE system, and these two are stable constant solution. Okay. So here we assume epsilon is sufficiently small. Then we can apply the singular perturbation technique to this problem. We can get the traveling wave solution. Okay. So here is a profile of a traveling wave solution U and B with velocity c. Okay. These states correspond due to constant stable solution, constant states. Okay. So here we use this moving coordinate. When c is positive, this wave moves to the right-hand side. Okay. So here is a solution branch of this problem, tau versus c. Okay. So c is the velocity of this traveling from solution. Okay. Here we assume f and z are orthosymmetric with respect to the origin. Then we can easily find there exists a standing front. Standing front means the velocity equals 0. There exists a standing front solution for all positive tau. So this is a branch. This is a global solution branch, tau versus c. Okay? Tau is a time constant, c is a velocity. This line, tau axis is a velocity equals 0. Then this branch corresponds to standing front solution. Okay? So when tau decreases, then there exists a tau naught at which new two solutions bifurcate to the left-hand side. Okay? One is a traveling front solution with positive velocity. The other one is a traveling front with negative velocity. Okay? So for the stability, we already know this and this, these three branches are stable, but this one is unstable. Okay, this is the case of homogeneous case. So in our PDE system, so-called pitchfork bifurcation structure appears. Okay, so next we introduce the heterogeneity in our system. Say we introduce heterogeneity, this diffusivity d of x like this. Okay. But simply d of x is a step-like function. Say 1 plus lambda time Heaviside function. Exactly on negative region d of x equals 1. On the positive region d of x equals 1 plus lambda. Okay? When lambda equals 0, this is a case of a homogeneous case, right? Then this lambda controls the strength of heterogeneity. Okay? So here's a picture of the d of x when lambda is negative. In this case, d of x jump down at x0 like this. Okay? So on the left half plane, d of x equals 1. So on this interval, this equation identical to the previous one here, this one. Okay? So when we fix tau less than tau naught around here, we have a stable traveling front with a positive velocity like this, propagated this way. This is the stable traveling front. There exists a stable traveling front solution when tau is less than tau naught. We use this as the initial data of this PDE system.
This is very interesting, but I want to ask you a question.
Uh-huh.
Why? Is there any intuition why the two organisms or two chemicals will do such a inhomogeneous dispersal with homogeneous environment? Because A and G are homogeneous. Is there any intuition?
Yeah. For example, media is inhomogeneous, so there's some kind of porosity is different. But chemical reaction same, I think.
Okay.
Okay.
Okay. Okay. Thank you. Yeah.
So, sorry. So, sorry. So we use this as the initial data of this PDE system, and we study the response of traveling wave solution and the interaction between traveling front and heterogeneity. Okay. So here is a numerical simulation. So we tried four types of value lambda, right? So when lambda equal minus 0.09, which implies heterogeneity very weak. Okay, so in this case, sorry, cannot do it. Okay, so so in this case, traveling from passing through passing through x equals 0 and then propagate to the right hand side. Okay, so we decrease lambda a little. Say, so when lambda equals minus 0.10, this is just by 0.01 from here. Okay, so which implies heterogeneity become somewhat stronger compared to this case. Okay, in this case, so traveling front move into the region x is positive, very around the positive area. So move into the positive region and then return to the left. So we sorry, I call this case a passage and this case a reflection. Okay, so lambda decrease more. Say lambda equal minus 0.12. Okay, so heterogeneity becomes even stronger. So in this case, traveling front blocked at x equals 0 with little bit oscillation. So we call this case stoppage or pinning. So finally, we decrease lambda more. Say lambda equals minus 0.16. In this case, traveling front reflect to the left-hand side without entering this positive region. Okay. So here is a bird's eye view of the previous numerical simulation. This implies a component U. Okay. So we assume epsilon is sufficiently small, then the component U has a sharp transition radius like this. Okay. So we call this line as the layer position of the front. Okay. So indeed, these two are both reflection case. So indeed, there are some difference between them. So we show this next slide. Okay, sorry. So this picture implies dynamics of a layer position are drawn in each case. So these two are diffraction type 1. Okay? In case B, layer position move into the region X positive, then return to the left. But in case D, layer position return to the left without entering this region. So we distinguish these two cases. So we got the 4 types of responses in our numerical simulation. Depends on the strength of lambda. Okay? So intuitively, it is easy for us to understand when heterogeneity is very weak, maybe pass through. It's very easy. Okay? Then heterogeneity becomes stronger. Something happens. For example, stoppage and reflection. Okay? But this case, in this lambda, there is a reflection type. Reflection exists between these two. Okay? These two. Okay? So this is very strange. The existence of this case is very strange for me. Okay?
Is there a lambda between these two that makes it stops?
Pardon? Lambda?
Some lambda between minus 0.09 and minus 0.1.
Yeah.
Between them, is there some case that it stops?
Yes. So it's my question. There is this case between these two. Okay. So recently, a method by which to study the dynamics of interaction between traveling front of pulse solution and heterogeneity was developed. So our study is motivated by a number of interesting studies like this. Okay? So 2002, A gives a general criterion on the dynamics of interaction, dynamics of weakly interacting, dynamics of interaction of traveling wave solution. Okay? So the other one is application of the first one. Okay? So these papers are very interesting, but these studies depend in part on numerical results because of their problems very complex. Okay? So the aim of this talk is to clarify the mathematically rigorous mechanism producing the 4 types of responses. That's the aim of this talk. So to understand this response in mathematically, we have to consider the dynamics of front solution in the neighborhood of a bifurcation point by using a center manifold theory. Okay? So here is our PDE system in homogeneous media. So this part is d of x. Okay? So we calculate this like this. So these parts are coming from heterogeneity. And the lambda controls the strength of heterogeneity. Okay? So for simply, we put this one as h sub 1 xu and this one as h sub 2 x of b. Okay? The first, let's consider the case of lambda equals 0, say homogeneous case. Okay? So this is the equation for homogeneous case. So we wrote this part as calculate pair of u. U has a 2 component like this. Okay? So for this PDE system, we can show the following results. So I said before, sorry. So still has a standard front solution S for any positive term because F and G are orthosymmetric. Okay? Furthermore, there exists a term naught, the positive number. At this term naught, linearize the operator calgraph L at S of x we wrote this one L. Okay? So L has two properties. First one says that L has a zero eigenvalue, the corresponding eigenvalue of derivative of S standing front. Next one says that zero is a there exists a function psi of x. This is a generalized eigenfunction of this L correspond to zero eigenvalue. Okay. Well, how about the spectrum L? Spectrum L contains two sets. One is a zero. The other one is completely left half plane in the complex plane. Okay. So property C1, C2 says that linearized operator is degenerate in Jordan block type at tau equal to tau naught. Okay. Since adjoint operator L, say L star, has the same property of L by using a Fredholm alternative, then there exists two functions, say phi star and psi star, satisfying the same relation for L star. Okay. So now our eigenfunction is not unique, so we fix this eigenfunction psi, phi star psi uniquely, we impose this normalized condition. Okay. So standing front has a translation free. Okay, so we fix the phase like this. So component U has a transition layer at z equals 0. Okay, we fix the phase of standing front solution. Okay, and we put tau equal to tau naught plus eta. Eta is a difference from the tau naught. Okay. Then we have the following theorem. Okay, our PDE system star has a solution E of Tx, which is approximated by this equation, this function, say L of x minus L plus R times the psi of x minus L. Okay, so for this S, x equals A is the layer position. And L and R the function of T, which satisfy these ODE system on the center manifold, two-dimensional center manifold. Okay. So here with a special nonlinear S and D, then we can calculate S and eigenfunction psi and eigenfunction of adjoint operator phi star and psi star. We can calculate exactly. Okay. And here is k of r eta. K is a cubic function of r. Here is m1 and the coefficient. Okay, so we can calculate this coefficient exactly like this. Okay, so we put this part as P sub 1 LR and this part as P sub 2 LR. Right? So by the results of stationary PDE problem, we can find there exists L1 star and L2 star. L1 star is negative, L2 star is positive, satisfying this equation. This means that previous ODE system has a constant solution, L1 star 0 and L2 star 0. So this system is quite complex, very complex. So we deduce some sense. Okay. So by using the scaling, control parameter alpha change to control parameter lambda change to alpha by using this relation, and we ignore higher order term of our ODE system, then we can get the lowest order ODE system like this. Here the time is a capital T by using this scaling. Okay. So x sub 1 and x sub 2 are coming from the heterogeneity, which is defined by this relation. So we can calculate these functions exactly. Here is the graph of h sub 1 and h sub 2. Okay? So these two are intersect at this point. This point is on this L-axis. This means that L1 star 0, L2 star 0 is a stationary solution, this reduced ODE system. Now we analyze this ODE system. Okay? So here's the same picture I showed before. So at that time we used this parameter lambda. So now we use scaling from lambda to alpha. Then this lambda change to this alpha. Okay. Right? So I showed our ODE system had a two constant solutions, say equilibrium point here and here. Okay, L1 star 0, L2 star 0 here. And blue one is for stability, blue one is the saddle point, and the red one is the stable focus. Okay, so black trajectory indicates a stable and unstable manifold of this equilibrium point. So this line and this line is a stable manifold, this saddle point, and this line and this line. This line and this line indicates the unstable manifold of this saddle point. Okay? So in each alpha, the situation is the same. But our system depends on alpha. Alpha changed, solution trajectory changed. But these properties not changed. When alpha decrease, solution trajectory around here a little bit go up. So in this picture, this point 6 point something, in this picture, this point 10 point something. So trajectory go up depend on this alpha. Okay? So dotted red line indicates a solution trajectory with initial data here. This initial data is the same as I showed before in the numerical simulation of PDE system. Okay, this is the same, not change, does not depend on alpha. Okay, so in this case, say when alpha equals this value, solution trajectory like this. So in this case, initial data locate above to this stable manifold. So in this case, similarly, initial value locate to the above this stable manifold. But in this case, solution trajectory move like this. In this case, move this way and enter this region L is positive and then return to the left. So in this alpha, initial data locate below this stable manifold, then this trajectory converge to this stable focus. So for this alpha, this initial data locate below the other stable manifold, locate below the other stable manifold, then this trajectory return to left. Do not enter this region.
So that's interesting. What's the so I can see the transition from A to B, B to C.
Yeah.
What is the transition from C to D? What's in between?
C to D?
Yeah, because I can see how things can change from B to C, right? Because this bump up. Why there's such a sudden change from C to D? That's my question.
Subtle change, yeah.
From B to C, I can see it. From the
B to C. This is B to C.
Yeah. I can see it,
okay.
Yeah.
Yeah. So that is the same, but location of the initial value is different.
I see.
Okay, so sorry.
Location.
Yeah. Okay, so this is my understanding with the point of view mathematical rigorous sense. So we understand completely. We have to determine the separate leaks of these two. Okay. So now let's consider the separate leaks of these two cases, these two responses. First, let's consider the separate leaks of these two cases. Okay. So for this case, you can easily see that this stable manifold, okay, of this point separate these two cases to the response because in this case initial data located above this line and this case initial data below this line. So this stable manifold is separated. Okay. How about this case? Okay. So for this case it is very easy. So in this case the other stable manifold is separate of these two because if initial data locate above this stable manifold, then reflection, and initial value locate below, then combine this one, the stoppage. Finally, what is the separate of these two? No trajectory drawn in this figure which separate these two. Okay. So the final question is what is the separator between the passage and the reflection type 1? Okay. So to give an answer, we introduce a bump type of heterogeneity like this. Okay. Here we use the bump type, so length of bump equal P. The other situation is same. Okay. So we try some numerical simulation. So for P equal to 0.0, length of bump is very small. In this case, there occur depend on this value, passage, blocked, reflection type 2, just like here. Right? And P become large, say the length of bump become a little bit large. In this case, we got a 4 case. Depends on the size of lambda. Okay, passage blocked reflection type 2. This block and blocked are different. So this is a stationary solution, right? This is a x-axis, this is a t-axis. This is a stationary solution. We superimpose these two solutions in same picture. So this is the picture. So different solution. Okay. Then these two are different. So we got a 4 responses in this case. Furthermore, we increase P more, then length of the bump is very large. In this case, here. In this case, depend on lambda, passage, reflection of type 1, stoppage, reflection of type 2. This is the quite same as the step case I showed before. Okay. So to analyze to this difference, we consider the ODE system on the center manifold. Okay. So let me show the reduced ODE system. Here is these parts are coming from the heterogeneity, but in this case we use the bump shape heterogeneity to calculate this function. Okay, so first let's consider a constant solution of this ODE system. So we put here 0 and 0. And from this relation, alpha equals this one, and we substitute this alpha here and here, we got this equation. Okay? So first we solve this equation, and then put here, and we got the constant solution. Okay? So then we consider f of L, the shape of f of L. So let's consider graph of f of L. So here is a graph of f of L. Okay. So we insert this case specially. So P is small. There exists three constant solutions. Blue one is the side of red one, the stable focus. Okay. So we increase P little. In this case, there appear 5 stationary solutions. Okay. And this red one become unstable, and the new solution appear in both sides. These are stable focus. Then, at some value, there occur supercritical pitch bifurcation phenomena occur at some value P. Okay? And when we increase P, number of constant solution is not changed, and stability also is not changed. Okay, so let's draw a solution trajectory for this case. So there are 3 constant solutions, blue one is the side ones. So then these trajectory are stable and unstable manifold, right? So in this case, so we got a numerical solution of 3 types, 3 types like this, right? So correspond this data, we solve ODE system. Then when alpha goes like this, then passage blocked return. Okay? Next, P equal 1.0. So this case, there are no stable focus, and this become unstable like this. And here is a stable and unstable manifold, and this is a bump region. Okay, so when we try the numerical simulation, we got a 4 type: passage, blocked, reflection type 2. So this case corresponds to in our ODE system here, and the first one, the passage, and the stoppage, the different stable solution. Okay? The other one, and the return, do not enter this region, say reflection type 2. Okay? So now P is 1.8. The solution trajectory like this. Here, blue one is saddle point, the red one is stable focus, and here is stable and unstable manifold. When P increases a little, say just 1.87, in this case, there is a connection orbit between these saddle points, so-called saddle connection. Okay, so when P is less than this value, in this case, this connection converges to this case. When P is greater than this value, say this one, this saddle connection, say unstable manifold this point, go to this way. Okay, so for some value of connection, and if P is less than that value, this right and this right. Right? So then so-called homoclinic bifurcation occur at this value. Okay. So in this picture, reflection of type 2 occurred, for example, here, but type 1 do not occur because if initial data here, this combine this one here and go away, then does not occur reflection type reflection of type 1 does not occur in this case. But after homoclinic bifurcation, there appears very narrow region. Okay. say here, they appear very narrow region. Then there exists a trajectory move like this, so-called reflection type 1. Okay? So for P is large, we got the 4 types of responses. This is the same as a step case. Stoppage, reflection type 1, passage, reflection type 1, stoppage, reflection type 2. So how about our ODE system? So this is a direct ODE system. Okay. So this case, passage, this one, reflection type 1, and this one is correspond to stoppage, and this one correspond to the reflection type 2.
So is it numeric simulation or it can be improved?
Yeah, we got the exact form of ODE system. Yeah. But we ignore some small part. We consider only a reduced ODE system, but the other one, the regular perturbation, a small one. Essentially, all situations determine this structure. Okay. So here is P equal 2.1. So length of bump is very large. Okay. So this here is a saddle point. Okay. So this stable manifold separate this and this. Okay. So let's go before. And here, okay. So these red lines separate this stable manifold. Okay. So above this stable manifold, then pass through, and below to this manifold, then return. So this is a stable, this is a separator of these two cases. So here is a same sketch. Okay. So in this situation, P tends to infinity. So this combines two cases of a step. Right? So when P tends to infinity, this unstable solution converges to a stable standing front solution here. Okay? So in our numerical solution, we fix here. Okay? Here is this branch unstable. This solution is an unstable front solution. So this solution, when P tends to 0, this solution converts to this one. Then, what is the separator of these two? So at L equal to infinity, there exists unstable standing front solution, and stable manifold separate these two. So this is our understanding. Okay. So another example, we can consider heterogeneity, for example, a double bump or multi-bump or periodic bump. Okay. So when we try some numerical simulation, there appear strange phenomena, say chaotic phenomena or chaotic phenomena or something. Okay. So I have to stop here. Thanks for your attention.